Hi and welcome back. In this video, we're going to talk about horizontal asymptotes of rational functions. So our motivation here is that we want to be able to describe the end behavior of rational functions, and the horizontal asymptotes help us to do that. So the idea is that we're going to look at the left-hand side and the right-hand side of the graph, which we represent as the limit as x approaches negative infinity of our function, and the limit as x approaches positive infinity of the function. So the negative infinity, x going to negative infinity, is the left-hand side, and x going to positive infinity is the right-hand side. So there are some standard rules we just follow to determine where the horizontal asymptotes are, but rather than just give you those rules without any explanation for where they come from, I'm going to go through some hopefully explanatory examples where we can see what's happening, and then at the very end we'll write our final rules. So I'm going to start with these three functions, and we're going to explore how their end behavior is different. So we'll do f of x equals x over 2x squared, we'll do g of x equals x squared over 2x, and we'll do h of x equals x squared divided by 2x squared. And we want to look at what happens as x goes to negative infinity and x goes to positive infinity of these functions. Remembering, we're trying to explain the end behavior, and we'd like to come up with some generalizations that we can apply to any rational function. So I'm going to fill out a table for these. We'll start with the function, then we'll talk about its end behavior, and we'll relate this to the horizontal asymptotes and the degrees of the numerator and the denominator. So we'll go through these one at a time and fill out the table together. So let's start with f of x. This is x over 2x squared, and I have the graph here. So as we look to the left-hand side, I'm seeing that the output values approach 0. Similarly, on the right-hand side, my output values also approach 0. So both our limit as x approaches negative infinity and our limit as x approaches positive infinity are equal to 0. So here we have a horizontal asymptote at y equals 0. So that end behavior where both of the ends are approaching 0 as the output, we write this as y equals 0, where y equals 0 is our equation of that horizontal line for the horizontal asymptote. Now let's look at g of x. This is x squared over 2x. So you'll notice that this rational function looks basically like a line with a hole in it. I'm using some really simple, honestly kind of boring rational functions to hopefully make a point. So here, let's look first as we go to the left-hand side. As x approaches negative infinity, our output values are going to continue to get more negative. So the function is going to go on and on downward, and so our limit is equal to negative infinity. There's no bound to those values at the outputs, they're just going to keep getting more negative as we go further and further left. Then on the right-hand side, we're doing the same but positive. So as our input values get more positive, our output values continue to grow and get more positive. So there's nothing stopping it from continuing to grow, and so this limit is equal to infinity. So the right-hand side goes to positive infinity, and the left-hand side goes to negative infinity. So here, we would say that there is no horizontal asymptote. Our output values are not approaching some value. They're just both going off to negative infinity and positive infinity. So this function has no horizontal asymptote. Then lastly, we have h of x. This is x squared over 2x squared. So again, this looks kind of boring. It's just a line with a hole in it. But you can see here that as we go to the right and the left, we're definitely approaching a value, since we're basically just staying at that value. Specifically, on the left-hand side, we're approaching or we're at 1/2, and on the right-hand side, we're also at 1/2. So both of our limits are equal to 1/2, and here our horizontal asymptote is just y equals 1/2. So this one's a little boring, but you can imagine we could recreate this, but just where the ends of the function behaved this way. And we're using this for illustration purposes. So this does have a horizontal asymptote. It's at y equals 1/2. So now we can go back to our table and fill in some information and hopefully create a pattern. So I'll put the end behavior in here, and then the horizontal asymptotes. So our first function had a horizontal asymptote at y equals 0. The second function did not have one, and the third function had one at 1/2. So this is specifically related to the degree of the numerator and the degree of the denominator, which is the main characteristic or quality that we changed between each of these functions. So for our function f, the degree of our numerator, that polynomial in the top part of the fraction, is 1. But the degree of the denominator, or the bottom polynomial, is 2. So here we would say the degree of the numerator is less than the degree of the denominator. And this led to a horizontal asymptote of y equals 0. Then when we swapped the degrees, we made the degree of the numerator 2 and the degree of the denominator is 1. We had no horizontal asymptote. So here, the degree of the numerator was 2, which is greater than the degree of the denominator, which is 1. So I compare the top degree, which is 2, to the bottom degree, which is 1. 2 is greater than 1, and there was no horizontal asymptote in this case. Here, I like to think that the numerator of the fraction is growing much faster than the denominator, and so we're just going to continue to grow without bound. So that higher degree means we're just getting bigger and bigger as the inputs get larger and larger, and so there is no horizontal asymptote. Whereas in our first function, f of x, that denominator degree is larger, and so we're going to be dividing by larger and larger numbers each time, which means we're approaching 0. Then our final case is more unique. Here we have both polynomials having a degree of 2. So the numerator has a degree of 2, and the denominator has a degree of 2. So here the degrees are equal, and this had a specific asymptote of 1/2. This is actually coming from the leading coefficients of the polynomials. So the numerator has a 1 in front, and the denominator has a 2. So this is the ratio of those leading coefficients. It's 1 divided by 2, and that's the horizontal asymptote. Here, basically, the numerator and the denominator are growing at the same rate, basically, and so it's just equaling out to be the ratio of the leading coefficients. So I want to generalize this with some final statements, and these are the rules you're going to follow every time you're doing a problem with horizontal asymptotes. So here is my general statement setup. I'm just going to repeat this same layout 3 times, once for each case. So first, if the degree of the numerator is less than the degree of the denominator, then there is a horizontal asymptote at y equals 0. Now we could say this for greater than. So if the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. And lastly, if the degree of the numerator is equal to the degree of the denominator, then there is a horizontal asymptote at y equals a over b. And specifically, those a and b are the leading coefficients of the polynomials. So the asymptote is at y equals a over b. All right, so those are our rules for horizontal asymptotes and a little bit about why they are the way they are. We'll do some examples in a later video. That's it for this one. Thanks so much for watching, and I will talk to you in the next one.